everyone. In this video, we will introduce some methods for working with categorical data. So now that we have really extensively studied how to model numerical response variables, let's flip it around just a little bit and think about categorical data. We'll start with the sampling distribution of the sample proportion p hat. So just thinking about a single categorical variable. We'll look at some confidence intervals for the population proportion p, as well as some methods that we can use to do a hypothesis test on the population proportion p. So let's start with an example. Advanced melanoma is an aggressive form of skin cancer that until recently was almost uniformly fatal. We have two therapies that have seemed to be successful in triggering an immune response. This one and this one. We'll say the N therapy and the I therapy so that I don't go crazy. A 2013 report in the New England Journal of Medicine by Wolchok et al. Reported the results in a study in which patients were treated with both drugs. 53 patients were given these new drugs concurrently, and response to therapy could be evaluated in 52 of the 53. Of these 52 patients that we could study, 21 of them, or 41%, experienced a response according to commonly accepted criteria. So in other words, they responded positively to these drugs. In previous studies, the proportion of patients responding to similar drugs was 30% or less. So how can we compare this new data to those previous results? Well, this type of variable is something that we refer to in statistics as a binary variable. So for us, a binary variable is one with only two possible outcomes, and we'll call these outcomes successes or failures. The outcome that we care about or that we want to see occur is typically referred to as a success. The other outcome or all other outcomes get lumped together as failures. Now, success doesn't have to be a bad or a good thing. Failure doesn't have to be a bad thing. It's simply, are these in the category that we care about? Yes or no? Now, when we have a variable like this, or a binomial variable, our goal is usually to estimate the underlying probability of success or the population proportion, which we will refer to as p. Now, the sampling distribution of the sample proportion p hat is going to be a good place for us to start. And it turns out that this sampling distribution has mean or center, this n times p. So we would expect, this should just be p, not n times p. So the mean of the sampling distribution is the population proportion p. The standard error of the sampling distribution is the square root of p times 1 minus p over n. Now, let's think about the shape of this sampling distribution. You'll probably will not be surprised to find out that, like the sample mean, the distribution of the sample proportion is also approximately normally distributed as long as the sample size is long enough. Now, different resources will give you different cutoffs for what a large enough sample really is. This is a good rule of thumb. So as long as n times p is greater than 10 and n times 1 minus p is greater than 10, our sample size is probably sufficient for normality to kick in. Again, this mean, it has a typo. This should be p, not n times p. Now, we can calculate confidence intervals and do hypothesis tests just using this normal-based approximation. And very often in practice, you'll see people do that. But when we can, now we're using computer-guided methods here like R, so we can be accurate, so let's be a little bit more accurate. Let's look at some methods based on a different distribution, the binomial distribution. So the binomial distribution is actually the true distribution of results coming from a binomial random variable. So specifically, the number of successes that we would observe in a sample X follows this exact distribution. Now, that's assuming that the probability of success is constant and that the sample size is fixed. Here is what this distribution looks like. So the probability of observing X successes is n choose x, so this is the number of ways that x successes can occur in a sample of n observations, times the probability of success p raised to the x power times 1 minus p, or the probability of failure, raised to the n minus x power. Now we won't do very many calculations with this binomial distribution directly, but it is nice to know what's happening under the hood when we start working with some data. Now this binomial distribution forms the backbone of two procedures that we'll talk about in this video: the binomial hypothesis test and the binomial-based confidence interval. So in order to work with this binomial distribution, let's take a look at what it actually looks like. So here you're actually seeing 6 different binomial distributions. The binomial distribution is not a continuous distribution. In other words, we have a discrete number of possibilities. If we are taking a sample of, say, 10 observations, we can only observe 0 success, 1 success, 2 success, 3 success, and so on. However, if we take a look at this binomial distribution, right away you might notice something happen. So as the sample size increases, here in the top row we have samples of size 10, bottom row we have samples of size 100, this distribution becomes a lot narrower really quickly in terms of the number of successes that we might observe. Now here I've increased, going from left to right, the probability of success. So on the left we have a situation where the probability of a success is only 10%, here 20% probability of success, here 50% probability of success. Look what happens to the shape of this distribution. It starts to take on a pretty symmetric bell-shaped curve fairly quickly. Now let's talk about how the binomial test is going to work. Like any other hypothesis test, there's essentially 4 steps. Step 1 is to write the null and alternative hypothesis. So we will assume that the true population proportion p is equal to some value, say p0. So our null hypothesis is that p is equal to p0. Our alternative is something else, either less than, greater than, or not equal to. Second step of any hypothesis test, identify the test statistic, or what you need from the data to get the test statistic. Here what we need are the number of successes, x, and the sample size, n. Alright, so step 3 is to calculate the p-value. So we will use the binomial distribution directly to calculate the p-value. Here's how we'll do that. We will plug this value from our null hypothesis, p0, into a binomial distribution. We'll build up that binomial distribution, assuming that the null hypothesis is true, and then we'll calculate directly from that binomial distribution the probability of observing a more extreme result. We'll do all of this in the background in R, so we won't do any of this calculation by hand, we won't see this process happening, but that is how the p-value is truly being calculated. So let's take a look at our report from the New England Journal of Medicine. Does it look like these new treatments are effective or helpful in looking at treating our patients? So starting with our null hypothesis, previous results showed that about 30% of patients would be expected to have improvement of symptoms. So we'll plug that past result into our null hypothesis, so p is equal to 30. If these new drugs are truly representing an improvement, then we should see an increase in the response rate. We should see more than 30% of patients have an improvement of symptoms. So we've got 2 test statistics here in our second step. We have the number of patients who improved, that is 21. We also have the number of trials, that is 52. What you're seeing here in this bar chart is actually the true binomial distribution. So I've calculated this for you off screen. What I've done is highlighted here in blue the part of the graph that represents a more extreme improvement. So starting at 21 successes, or 21 patients who improve, and then anything higher than that. So just guesstimating this, it looks like the probability that 21 patients or more would improve, if this true improvement rate is only 30%, is probably pretty small. We'll calculate it directly using a function in R called binomial.test. Now there are 4 to 3 inputs depending on how you want to use this function. If we're using binomial.test to do a hypothesis test, we'll need to enter the number of successes, that's our x, the number of samples, or the number of observations, that's our n, the value from our null hypothesis, here that is p, and the desired alternative, which is greater. So here it looks like there's a p-value of about 0.07. So maybe there's some evidence of improvement, but certainly not very strong evidence. Again, like any other hypothesis test, we will build our interpretation in the same way. So if the p-value is sufficiently small, we'll say that there is strong enough evidence to reject the null hypothesis. If the p-value is large, there is not enough evidence to reject. Again, as before, sample size matters, quality of the data matters, consequences of errors matter as well. So this should not be a black and white decision about whether to reject or fail to reject. Let's take a look at another example. Male radiologists have long suspected that they tend to have fewer sons than daughters. Now they are, through the routine performance of their job, highly exposed to radiation as X-ray technicians. I will let you imagine in your own head the effect that this could have. In a random sample of 87 children of, quote, highly irradiated male radiologists, so ones that had experienced quite a bit of exposure over their careers, 30 of those children were male. We'll assume that the population proportion of male births is 51.9%, which is pretty close to the human population. Male babies are slightly more likely. Is there significant evidence to show that male radiologists are less likely to have male babies? Well, let's take a look at our hypotheses. If male radiologists are exactly the same as the rest of the population, if there's been no ill effects, then the true proportion of male births should be 0.519. If they're less likely to have male babies, our alternative should be less than 0.519. Our test statistics are the number of male births, so x equals 30, our sample size, n equals 87. We will plug all of this into that binomial.test function. At home, take a moment or two to think about how you would complete this. Here's the code that we would need to write. So our number of successes, x is 30, our sample size n is 87, our hypothesized value p is 0.519, our alternative is a less than alternative. Looking toward our p-value, this is very low. We have 0.0008. So yes, it looks like there is significant evidence to show that male radiologists are less likely to have sons. We will reject our null hypothesis. Now, let's talk about the standard error here for just a moment. Let's estimate the standard error of the sample proportion of sons born to male radiologists. So we'll use our sample proportion here as an estimate to get an idea of what the standard error truly is. Our estimated standard error turns out to be 0.05. So we estimate that we're about 5% away from the true population proportion. Now, how do we turn that standard error into a confidence interval? We're actually going to have two choices with this sort of situation. One choice is a familiar choice. This is the standard or the walled confidence interval. Here we're basing things on the normal approximation to the sampling distribution. So essentially adding and subtracting about 2 standard errors. Another option is to use what's called the Klopper-Pearson confidence interval. Now this Klopper-Pearson confidence interval, like the test that we just did, is exactly based on the binomial distribution. So it can be more precise in that way. So let's start with the walled confidence interval. This is calculated just like that original confidence interval that we began with from the normal distribution, we'll take our sample proportion, add and subtract 1.96 times the standard error. If we have a relatively large sample size, if our sample proportion P isn't too extreme, this tends to work pretty well. However, it can fail for small samples and for P close to 0 or 1. So that is a caution with this confidence interval. The upside is that this confidence interval is fairly simple to calculate by hand. So let's calculate this interval. We've got our standard error. We've got 0.05 for that. We'll add and subtract 1.96 times the standard error to our sample proportion P hat. So we get 0.345 plus or minus 1.96 times 0.05. So we get a confidence interval here that ranges from about 2.45, or 0.245, excuse me, to 0.445. So we're estimating that somewhere between 24.5 and 44.5% of babies born to male radiologists will be boys. Now, let's take a look at this Klopper-Pearson interval. The idea here is very similar to the idea of the binomial test. Essentially, what we will do is take all of the values of the binomial distribution, specifically the binomial proportion P, all of the values here for which we would fail to reject this null hypothesis in a two-sided hypothesis test become the confidence interval. This is also referred to as the exact binomial confidence interval because it's based on probabilities taken exactly from a binomial distribution. Now, this is incredibly difficult to calculate by hand, but quite easy if you're working in R. We'll use that same binom.test function. Instead of giving a null and alternative hypothesis, we'll just provide a confidence level. So here, a 95% confidence interval based on the binomial distribution goes from about 0.246 to 0.454. It is slightly different than the confidence interval that we calculated by hand using the normal distribution. They're different, but they're not that different. There are other confidence intervals that we could use. However, as the sample size n gets larger and larger, these confidence intervals all tend to converge. What we mean by that is that after a while, as your sample size gets big enough, it doesn't really matter which method you choose. You end up in about the same place. So let's calculate a walled confidence interval and a Klopper-Pearson confidence interval for our first example, looking at improvement of patients given to drugs. Let's see if they're similar for this example too. So we'll calculate and interpret the walled confidence interval first. Here you can see that I've actually used R just like a calculator to do this calculation for me. So my sample proportion P is 21 out of 52. My sample size N is 52. So my sample proportion P plus or minus 1.96 times the standard error. I get a confidence interval that goes from 0.27 to 0.54, rounded to 2 decimal places. Using the Klopper-Pearson method or the binom.test method, we enter in our number of successes, our sample size, our desired confidence level, and we get a confidence interval that goes from 0.27, so the lower limit is nearly identical, to 0.55, so the upper limit is a little bit higher. Now, this is a relatively small sample size. This is a sample of 52 observations. Our confidence intervals are in near agreement. So either way, you get roughly similar intervals. We will stop here. In the next video, we'll take a look at how to calculate confidence intervals specifically to compare two proportions. I'll see you then.